next speaker, Gregg A, from the Royal Military College of Canada, and studies stellar magnetism across evolutionary time scale.
Thanks very much. I gather that's my cue to go ahead. So it's my understanding I've got 60 minutes, including questions. Is that correct?
Yes, exactly.
Awesome. Thank you. All right. So first, let me thank you very much for the invitation to provide a presentation at the Coloquio Nacional. I really appreciate the offer, and I thank in particular Laurence Sabin for contacting me. So I'm going to try and provide you with a little bit of a taste of my research and how it connects to polarization in general today. My talk will be in English. My Spanish is very limited, I'm afraid. Solamente un poco. And I will apologize in advance. I'm recovering from coronavirus, and so my focus may not be quite what it normally is, and my voice is a little bit ragged. So this is work that's been carried out with a number of individuals. I know that Colin Folsom is on this call, but I would like to highlight in particular these two. James Barron is a PhD student under my supervision at Royal Military College of Canada and Queen's University in Kingston, Canada. And I'm going to be describing some of his recent work exploring the magnetic fields of Cepheid variable stars. I'd also like to thank Etienne Boucher, who was an undergraduate thesis student a couple of years ago, who did some of the work on blue supergiants that I'll be showing you today. So I'm going to start off with a little bit of mathematics, not because I really enjoy mathematics, but because I think there's actually some insight to be had from this particular equation. So this is the so-called dynamo equation, and it's framed in a particular way for the stellar context. It describes the evolution of a magnetic field as a function of time under the influence number of phenomena. In this particular frame of the equation, the first term corresponds to rotational effects in large-scale circulation currents. And the second term corresponds to convection and turbulence. And these are the two terms that we tend to think about when we think about stellar dynamos, the production of magnetic energy through the conversion of mechanical energy via Ohm's law. And you'll notice that both of these terms are additive. They both have positive signs in front of them. And so in principle, they generate magnetic field in the presence of some initial seed field. But what's probably less known is this third term, which has a negative sign in front of it and actually corresponds to resistive decay of the magnetic field, because even though stars are highly conductive, they're not infinitely conductive. So it's interesting to explore this last term. And if we perform a little bit of mathematical magic with this equation, assuming that there are no large scale or small scale circulation currents taking place, we can demonstrate that that final term can be framed in terms of a diffusion equation. And so we can think about the magnetic field within a star as a slowly diffusing quantity, kind of like a drop of ink in a glass of water. And it turns out that the diffusion time scale that's associated with this equation is a function of the typical length scale of the magnetic field, which is roughly the radius of the diameter of the star, and the so-called magnetic diffusivity, which is an inverse function of the conductivity of the plasma. And so the details aren't particularly important, but of course we know that stars are big and they're highly conductive. And that means that if I take a magnetic field and I implant it in a star, even in the absence of any significant motions within that star, that magnetic field is going to live for a long time. In fact, if you throw in typical quantities for L and for eta here, the time scale is of order 10 to the 8 or 10 to the 9 years for a dipolar component of a magnetic field. And so what this tells us is that in addition to magnetic fields that are generated contemporaneously by motions within the star, what we call dynamos, we can also have magnetic fields that are expected to be stable and long-lived in regions that don't undergo such motions. And so this sort of insight is what leads us to the magnetic HR diagram that we understand today. And on that diagram, there are two basic modes of stellar magnetism that trace rather strictly the exterior structure of stars. On the right-hand side of the HR diagram, where stars are cool and tend to have convective exterior envelopes, we witness dynamo-generated magnetic fields in their exteriors, magnetic fields that, in many ways similar to the sun, tend to be cyclical, tend to be variable on a variety of timescales, and tend to be characterized by relatively strong small-scale magnetic fields and relatively weak large-scale magnetic fields. On the other hand, on the left-hand side of the HR diagram, we have stars that are sufficiently hot that hydrogen convection doesn't occur within the star's exterior envelope. These are stars with radiative envelopes near their surfaces. And these stars demonstrate magnetic fields that we refer to as fossil fields that correspond to the slowly decaying remnants of magnetic field that was generated sometime earlier in their evolution and correspond to that diffusion term in the dynamo equation. So a lot of my work deals with understanding how magnetic fields evolve as stars themselves evolve. And what I'm going to be exploring today is the idea that some relatively high mass stars, stars that begin their lives typically as B stars or O stars on the main sequence, ultimately evolve across the HR diagram and develop eventually convective envelopes. And so their external structure changes. And in doing so, their exterior magnetic properties change as well. And so I'll be talking about that in a couple of contexts today. But all of this, of course, is superficial. That is, we're referring to magnetism that's observable at the surface of the star. And it's important that we remember that even though a star may begin its life with a radiative envelope near its surface and a convective core in its interior, as it evolves across the HR diagram, that structure is going to change. And so if this star on the main sequence happened to have a fossil magnetic field in its radiative envelope and was generating a dynamo in its convective core, as it evolved to the base of the tip of the red giant branch, that same star may have consumed that original fossil magnetic field as the seed for a new dynamo in its exterior. And the dynamo magnetic field that was originally generated in its interior may have relaxed into a fossil in its interior. And so we can think about magnetism in stars as an evolutionary phenomenon that impacts the star not only at its surface, but also throughout its entire interior. And so this frames the basic focus of my research. I tend to focus on two different questions. First, how magnetic fields transform over evolutionary timescales as stars grow, cool, and change their interior structure, particularly near the surface. And the second kind of question that I look at is, what is the quantitative impact of those magnetic fields on stellar evolution, both at the surface via their interaction with stellar winds, for example, and in the interior as mechanisms for example, arresting convection and circulation. So I'm going to say a few words about how we measure stellar magnetic fields nowadays. This is a small piece of a high-resolution spectrum obtained with a spectropolarimeter called Espedant at the Canada-France-Hawaii telescope. This is the Stokes eye spectrum, and you can see here 3 spectral lines, all of which I believe are due to singly ionized iron. And in this particular star, the magnetic field is sufficiently intense that each of those lines is split into 3, or in this case, 2 Zeeman components. So this is the way that we're all familiar with for measuring stellar magnetic fields. But the reality is that most stars rotate sufficiently rapidly that these Zeeman components become blended together, and detecting the splitting in the Stokes eye spectrum is particularly challenging. So instead, we use the polarization characteristics of the Zeeman effect, in particular the circular polarization of the sigma components of these spectral lines, in order to infer the presence of a magnetic field and generally to perform modeling. So what you'll notice here is that each of the exterior components of the Zeeman patterns of these spectral lines is circularly polarized, one left circularly polarized, one right circularly polarized. The polarization, that is the orientation of these Stokes V Zeeman signatures, is the same for each one of these spectral lines. And the amplitude of the signature varies as a function of the strength of the spectral line itself. So even in the case of a relatively rapidly rotating star, because of the change in sign of the circular polarization, these Zeeman signatures remain detectable. And so this is our principal diagnostic of magnetic fields in the large majority of stars that have been studied to date. I will point out that it is beneficial to be able to measure both of these, because in the case of the Stokes eye spectrum, where the splitting is a function of the modulus of the magnetic field. So it tells us about the total strength of the magnetic field in the line forming region. On the other hand, the Stokes V Zeeman signatures, these things up here, are only a function of the line of sight component. And so they can cancel on small scales. And so it's important to realize that they're only telling us generally about the large scale pattern of the magnetic field. So just to give you a feel for how we infer information about the geometric structure of stellar magnetic fields, I'm going to use this, this numerical model, this movie, to first demonstrate to you that if I implant magnetic fields on the surface of an imaginary star, those regions of magnetic field generate Stokes V Zeeman signatures, and in the presence of rotation, experience a Doppler shift as those regions move across the disk of the star. And if you look carefully, you'll probably notice that the orientation of the magnetic field in each one of these spots is slightly different, and that induces a slightly different pattern of change of circular polarization as the signatures move across the stellar disk and hence through the line profile. And so there's a tremendous amount of information, both in terms of the orientation of the magnetic field, as well as its location on the star, that's encoded in a time series of circular polarization profiles. And so if we wish to obtain information about the geometric structure of the magnetic field of a star, typically we would observe that star as it rotates and obtain many observations at many different phases of rotation. We then use those observations in a procedure that I think was described in some detail this morning, whereby we reconstruct the field based on an inverse procedure, which is basically a multi-parameter optimization exercise. And that provides us with an estimation of the local strength of the magnetic field in terms of its vector components. In this particular case, the radial, meridional, and azimuthal components of the magnetic field, where the color scheme here is illustrating the strength of the field as well as its direction relative to the surface. And each one of these frames is showing us a little bit more than one hemisphere of the star viewed from the north rotational pole. In some cases, when we have sufficient information, it's possible then to take those two-dimensional maps and under reasonable theoretical assumptions, extrapolate the magnetic field in order to understand, for example, the chromosphere of the star or the star's magnetosphere. So this is a very high-level description of how we infer information about the magnetic fields of stars from the most detailed level down to the simplest case in which we simply have information about the presence of a magnetic field. So I mentioned that the spectrum that I showed you earlier was obtained with the Espinal instrument of the Canada-France-Hawaii telescope. This is the CFHT, located on top of Mauna Kea on the Big Island of Hawaii, likely the most beautiful emplacement of an observatory that I am aware of. This is the 3.6 meter CFHT. This gentleman is standing underneath the telescope where is located a Cassegrain polarimetric unit. That polarimetric unit has the capability of analyzing the polarization of incoming starlight, either in circular or linear polarization. After analysis, two beams leave the polarimeter and travel via optical fibers into the high-resolution spectral polarimeter, or the spectrograph located in a Coudet room underneath the telescope. This is an illustration of what we might see on the CCD. So you can see the individual spectral orders that have been folded by the prism within the spectrograph. And then if you look at the inset, you can see that each one of those orders is actually doubled because each one corresponds to a different orthogonal state of polarization. And then I suspect that everybody in this particular audience is familiar with the idea that then we can take those two cross-dispersed orders, extract them as intensities, and by summing them, obtain the Stokes I spectrum, and by taking their difference, obtain the Stokes V spectrum. Now, what I've described here is actually a simplification of the procedure because, as again, many of you will know, because of changes in the sensitivity of the CCD at different locations, as well as variability of both our instrumentation and our stellar subject as a function of time, simply taking a single exposure and calculating Stokes I and V typically results in systematic errors. And so we actually use typically a sequence of 4 observations of a single star in which the angle of the quarter wave retarder is rotated by 90 degrees between each sub-exposure. And that allows us to remove, to first order, both spatial systematic errors within the instrumentation as well as temporal systematic errors. Okay, so with that introduction, let me tell you a little bit about what we know about stellar magnetism on the HR diagram today. I think it's fair to say that there's been a literal explosion in our understanding of stellar magnetic fields since the introduction of the first high-resolution spectropolarimeters for stellar studies in the late 1990s. Nowadays, we know a tremendous amount about stars on the main sequence. And as I pull these up, I'll just remind you, I'm going to color code these according to the character of their magnetic field as we've inferred it. So we know lots about stars that are located on the main sequence around the location of the sun. So stars with spectral types of G and K. There have been a number of extensive studies exploring the different properties of M dwarfs with fully convective and partially convective envelopes. A tremendous amount of work has been done by John Landstreet, by the group at the Special Astrophysical Observatory in Russia, and my own group, trying to understand the fossil magnetic fields of A, B, and O type stars. There's been work carried out by, in particular, Evelina Lesian as part of her PhD thesis, and subsequent work looking at magnetic fields of pre-main sequence Herbig AE and BE stars. And similar work has been carried out by Donati and others on T Tauri stars. A lot of work has been published over the past 5 to 10 years by Michel Aurière and Renata Konstantinova and Tova, studying the magnetic fields of red giant stars, particularly stars that have masses that are similar to those of the sun. Laurence has published some excellent work describing the heretofore not well understood magnetic fields of AGB stars and other evolved late type stars. There's been some work on red supergiants, the coolest supergiants, initially by Jason Grunhut in 2010, and more recently by Michel Aurière and Matthias et al. Over the past few years. And then, and this relates to material that I'm going to be discussing today, there's been some work on blue supergiants, both near the main sequence and far from the main sequence, by Jean-Claude Bourret, by Aurore Blazer as part of her PhD thesis, and through a project called LIFE that was initiated by Coralie Niner a couple of years back. There's also been some work done on Wolf-Rayet stars, so the evolved descendants of the most massive stars. And so what I'm going to be talking about today, because this is a huge parameter space, is basically this green circle. I'm going to be focusing on stars that begin their lives with masses between about 5 and 15 solar masses. So these would be B stars on the main sequence, and then thence evolve across the HR diagram, becoming blue supergiants, potentially yellow or red supergiants, and likely ending their lives in the majority in supernovae. So I'm going to start with magnetic B stars on the main sequence, because this is the source population of the stars that we're going to be discussing. And I'm showing here an HR diagram that illustrates the entire sample of known higher mass, that is larger than about 5 solar masses, magnetic B stars that were known in 2018. This is part of Matt Schultz's PhD thesis. And you can see that this is a sample of about 50 stars. They range in mass through the mass range that I described earlier. They span the entire main sequence. In many ways, these are stars that, apart from the presence of their magnetic fields, are very similar to their non-magnetic main sequence brethren. Matt's carried out significant studies of the population characteristics of the magnetic fields of these stars. So, for example, we know the distribution of the magnetic field strengths of these objects. Their magnetic fields are by and large dipolar. They're inclined to the rotation axis of the star, and they tend to have strengths that are a few kilogauss. So the mean magnetic field strength of these stars at the dipole pole is about 3 kilogauss, with some significant range, ranging down to a few hundred gauss and ranging up to perhaps 10 to the 4 or 10 to the 5 gauss. And so Matt was actually able to carry out some interesting investigations of the evolution of these stars on the main sequence. It seems reasonable that if a star has a magnetic field that's embedded in it and is subject to decay, that it should also be subject to evolution responding to the evolution of the star as well. And we all know that as a star moves from the zero age main sequence to the terminal age main sequence, it expands. And so naively, that causes us to think that the surface magnetic field of the star, due to conservation of flux because of the frozen in nature of the magnetic field, should become weaker. And that's exactly what Matt observed. So this is a plot of the inferred magnetic field strength of many stars from this sample that are shown as circles. This is the logarithmic strength of the field, and this is their fractional age relative to the terminal age main sequence. So this is the ZAMs, and this is the TAMs. And you can see that there's a general trend for the magnetic fields of these stars to become weaker statistically as we approach the TAMs. These two pink curves correspond to models of field evolution of stars, making different assumptions about how the field should evolve. And so we can already see there's some reasonably compelling evidence that magnetic fields of stars evolve on the main sequence. And so the influence of the magnetic field on the star and its exterior probably changes as the star moves from being relatively young to being relatively old. So this is a clue for us, and it motivates us to want to understand not only how the stars behave on the main sequence, but how they behave after they leave the main sequence. So if we imagine a star that completes its hydrogen burning and evolves along its evolutionary track through the Hertzsprung gap, perhaps to one of the blue loops, we can ask ourselves a number of questions. What are the topologies of the magnetic field? Does the magnetic field change in character? That is, does it change from being a fossil magnetic field to a dynamo magnetic field? And what are the population characteristics of those fields? So how does this distribution of field strengths transform into a new distribution as the stars make their way onto the post-main sequence? And through back of the envelope calculations, we can already provide ourselves with a little bit of guidance about how that might work. So if we continue to think about the fact that stars are highly conductive and that fossil magnetic fields are frozen into the star and so are likely to weaken as the star expands, then we can take Alfvén's theorem and through a very simple back of the envelope calculation and taking some initial conditions about the strength of the magnetic field on the main sequence, the size of the star on the main sequence, and the post-main sequence size of the star, we can provide an order of magnitude estimation of how strong the magnetic field should be as the star grows and finds itself in the blue supergiant phase. And in this case, for these particular parameters, it turns out to be about 10 Gauss. So we've actually carried out searches for such magnetic fields. So we're going to be talking about going from, but before I talk about that, I'm going to tell you a little bit about magnetic properties of B stars on the main sequence. So we've already talked about the distribution of field strengths. From my perspective, one of the most interesting phenomena that results as a consequence of the presence of a magnetic field at the surface of a B star on the main sequence is confinement of its stellar wind. So this is principally a consequence of the interaction via the Lorentz force between the magnetic field suspended above the star and the ionized stellar wind leaving the star. As the wind attempts to leave the star, it travels along closed loops. In both hemispheres, it travels to the loop apex where it shocks, And then that material cools while emitting in a number of different spectral bands, and ultimately generates in the steady state co-rotating magnetosphere around the star, which can be probed through spectroscopy as well as through photometry. I'm not going to spend a whole lot of time talking about the dynamics of these magnetospheres, but they're extremely interesting from the perspective of a multispectral study. We've done a lot of work examining the optical spectra of these stars and studying the structure of the magnetic field based on the rotational modulation of diagnostics like H-alpha and the helium-24686 line. But they're also emitters and variables, both in the ultraviolet as well as in the X-ray. And we recently done a significant amount of work studying these magnetic fields using gyrosynchrotron and auroral emission in centimeter and long wavelength radio. Okay, so we've talked about the main sequence. Let's move on to the post-main sequence. And here I'm going to be talking about blue supergiants. So these are the evolved descendants of our main sequence B-type stars. They typically have spectral types between A7 and early B. They're going to be located either in the Hertzsprung gap or at the end of the blue loop, so at temperatures that are higher than the Cepheids that we're going to be talking about later. And they typically have surface gravities that are about a factor of 100 lower than they had on the main sequence. So the first explorations of magnetic fields using modern instrumentation that I'm familiar with was a study by Matt Schultz back in 2014, back when he was completing his master's thesis. He looked at a number of very bright supergiants in the sky. You'll recognize the names of all of these because they're all naked eye stars. And he obtained what at the time were unprecedentedly precise measurements of the magnetic fields of these stars. So you can see that the uncertainties were of the order of 1 Gauss. Unfortunately, as you can see in the circular polarization spectra at the top here, no magnetic field was detected. There's no evidence of a field. And so this was followed up by Coralie Niner and our collaborators over the past few years. And I'll just remind you, right, we're looking at magnetic fields that are kind of the order of 10 Gauss, and we're not seeing them. So both Coralie and then Alex Martin, who was her postdoc, obtained some initial observations in the context of the LIFE program of a couple of A-type supergiants. This is Iota Car, this is 19 Origi, and obtained the very first detections of magnetic fields in these blue supergiants. And what was interesting is that notwithstanding the fact that Matt Schultz had obtained unprecedentedly precise observations of the stars that he studied, Coralie needed to go about an order of magnitude deeper in order to detect these magnetic fields. So these are fields, as you can see, that are about an order of magnitude less intense than what we might have assumed from our back of the envelope calculation. And that could have a number of explanations. I won't go into those right now, but if you want to save it for a question at the end, I'll be happy to address it. So with the demonstration that magnetic fields can be detected in blue supergiant stars, we started to collect a sample of stars for which magnetic fields are detected. So once again, this is an HR diagram. Each one of these evolutionary tracks is color-coded according to mass. The dashed ones correspond to a model that's rotating initially at 40% of the star's critical velocity. And for reference, the solid lines are non-rotating models. And so you can see that all of the stars in which magnetic fields have been detected among the blue supergiants nowadays have masses that are probably between about 5 and perhaps 12 solar masses. As I mentioned, these stars are either present within the Hertzsprung gap or more probably located at the end of a blue loop. And these stars range in temperature from about 10,000 Kelvin down to a little bit less than 7,000 Kelvin. Here are a couple of stars that have been studied by Etienne Boucher that I mentioned at the beginning. These are new detections that haven't been published yet. This is Eta Leonis, one of the stars that had been observed by Matt. By obtaining an error bar 3 times smaller than Matt's, we're able to detect an unambiguous Zeeman signature in the spectral lines of this star. Alpha Lep is a somewhat cooler blue supergiant with an F0 spectral type. Again, a very clear detection. Alpha Pur is a star for which we've obtained a large number of observations. You can see them stacked here. And what I'd point out is that the morphology of the Zeeman signature changes as a function of time. I'd also point out that it's quite complex with a number of crossings of the zero line. This is somewhat reminiscent of a dynamo-generated magnetic field, and that would be consistent with this star's relatively late spectral type. So this could be an example of a star that, notwithstanding the fact that it began its life as a B star in the main sequence, now has a sufficiently convective envelope that its magnetic field is generated primarily by a dynamo. In contrast, here's 13 Monocerotis. It's a relatively hot A0 supergiant. We've detected it at 3 or 4 different epochs. And what I want you to notice is that it has a relatively simple Zeeman signature corresponding to a relatively simple magnetic field structure. And over the course of its rotation, you can probably see that the star actually changes the polarity of its Zeeman signature from positive on the left here to positive on the right, likely here. And that's suggesting to us that this is more likely a fossil magnetic field, and we're seeing rotational modulation like in the main sequence B-type stars. So I'm going to come back to the magnetic HR diagram that we saw earlier. I didn't emphasize it, but this orange line here essentially delineates the region of the HR diagram where significant external convection is present and the region where significant external convection isn't present. And so we can think about our HR diagram of the blue supergiants in a similar way. So that same delineation occurs about here. And so it seems likely that within our population of stars, that we can probably identify individual objects that have fossil magnetic fields and other stars that are somewhat cooler that likely have dynamo magnetic fields. And so one way of exploring that, of course, is to use state-of-the-art stellar structure and evolutionary models to study convection within the star and to infer whether or not a dynamo could be sustained in the outer layers of individual objects. Okay, so I'm going to move along. So we talked about main sequence B stars and the characteristics of those stars either within the Hertzsprung gap or at the tips of the blue loops. I'm going to focus now on a particular group of stars that, while deriving from the same initial population, are of particular interest from a cosmological standpoint. And that's the classical Cepheid variables. So these are stars with masses typically between about 5 and 12 solar masses, began their lives as main sequence B stars, that as they travel through their blue loops are found in the instability strip. They typically have temperatures around the temperature of the sun, maybe a little bit hotter. And of course, they're characterized by their periodic pulsations, which are strongly correlated with their luminosities and define the period luminosity relation. So it's interesting that a couple of these stars, a couple of Cepheid variables, are known to be non-thermal emitters in the ultraviolet and in the X-ray. What's being shown here is a summary of results from Engel et al. 2017 for Delta Cephei, the canonical Cepheid. The bottom panels show the photometric radial velocity and radius variation of the star as it goes through its pulsation cycle. What's most interesting is, in particular, this panel here, where we have flux measurements obtained with XMM and Chandra that show that this star undergoes a brightening in X-rays around the time of its maximum radius. And so this caused us to ask the question whether these stars exhibit, for example, reconnection of magnetic fields as they expand and their atmospheres undergo velocity fields due to shocks propagating through. But it was a hard question to answer because up until very recently, we knew almost nothing about magnetic fields in Cepheid variable stars. Jason Grunhut, in his seminal study in 2010 of cool supergiants, observed Delta Cephei, but didn't obtain a detection of any magnetic field. He did, however, obtain a detection of one Cepheid variable, and that was Eta Aquila. And you'll notice that Eta Aquila has a Zeeman signature that has a very strange shape. I'm going to be returning to that in just a few minutes. So it was clear that the time was right for a deeper investigation of the magnetic fields of Cepheids. And this was about the time that James Barron was beginning his PhD. So James has been carrying out a magnitude limited survey of about 25 relatively bright Cepheid variables that span the mass range of stars that we've been talking about today. Some are located in the Northern Hemisphere, some are located in the Southern Hemisphere. And he's been using the Canada-France-Hawaii telescope in Espinal, as well as HARPS pole on the 3.6 meter telescope at Lucia, to observe this sample of stars over the past couple of years. And he's made really significant progress. He's observed the majority of his sample at this point, and not surprisingly, some of these stars don't provide any detection of a magnetic field. Other stars provide very clear detections of magnetic fields, and the morphologies of those Zeeman signatures are in reasonable agreement with what we'd expect from Zeeman effect, due in this particular case to a relatively complex magnetic field. Others, on the other hand, have really strange Zeeman signatures, signatures that are reminiscent of that of Eta Aquila, and that absolutely cannot be reproduced under the auspices of normal Zeeman effect. So this is a summary of the stars that he had detected maybe as of 6 months ago. I think he's got a couple more detections now. You can see that there's a significant diversity of Zeeman signatures in the different stars, which is probably telling us something about the different influences that the star's atmospheric dynamics have on their magnetic fields and the expression of the magnetic field due to the Zeeman effect. And you can also see that these stars correspond to a range of masses and locations throughout the instability strip. So I'm going to take a couple of minutes and talk to you about what I think is one of the most interesting detections that James obtained, and that's in Polaris, the North Star. James has been observing Polaris for a little over a year now. And so he's obtained observations that span a significant period of time. And this is an overplot of the Zeeman signatures from 2020 to February of this year. And you can see that there's definitely some modulation, some evolution of the Zeeman signature that is probably telling us to some extent about the evolution of the star's magnetic field. At the same time, these are complicated objects. So in the upper panel here, I'm again showing an overplot, but now these are observations that are obtained nightly over the course of a 7 or 8 night run in November of 2021. Right, so Polaris is a big star. It's not rotating particularly quickly, and because of the size of the star, its magnetic field isn't evolving intrinsically very fast on the large scale. What we're seeing here, the differences between these Stokes V profiles, is due to modulation due to pulsation of Polaris. And so that's a demonstration that in order to be able to model and understand the magnetic fields of these stars, it's a far more involved process than that which I described earlier, where we can describe the star as a two-dimensional ball with a static magnetic field. In this case, we need to take into account, at minimum, the pulsation of the star and the radial velocity changes of the V and I profiles as the star pulsates, in addition to potential changes in the magnetic field, and quite probably the dynamics of the atmosphere that are going to have an effect on the local line profiles. So that's all work in progress. James has also come back to addressing the original question, which is these non-thermal effects in the atmosphere, in particular of Delta Cephei. He was able to obtain a 7-night-long time series of observations of Eta Aquila. So each one of these profiles corresponds to Eta Aquila observed on successive nights. The pulsation period of Eta Aquila is 7 nights long. So this is basically one full pulsation cycle. You can see the radial velocity motion of the line profile as the star pulsates. And then on the right-hand side, you can see the Stokes V signature of the star as the star goes through its pulsation cycle. And you can see that it's not only shifted, but its morphology changes as well. The relative amplitude of the two lobes changes, sometimes disappearing. And so trying to understand the formation of these profiles and whether their modulation can give us any information about the behavior of the atmosphere of the star is, again, work that's ongoing, part of James' PhD thesis. So as I wrap up, I'd just like to talk a little bit about the philosophy of studying samples of stars at different stages of stellar evolution. I like to think of this as a biography of stellar magnetism, where we have a star that begins its life on the main sequence, and then through studies of samples of stars, perhaps at the terminal age main sequence, at the top and bottom of the red giant branch, through blue loops, and ultimately up the AGB, we're able to loop back to the figure that I showed you at the beginning of the talk, and understand how magnetic fields of individual stars, as expressed through the characteristics of samples of stars with similar properties, evolve over the course of their lifetimes. We've started a little bit of this work on the theoretical side by developing grids of models of stellar evolution for higher mass stars that include the effects of surface magnetic fields. So this is work that was carried out by Joel Castelli as part of his PhD thesis back in 2019. And what he did was to include the effects of the interaction of the stellar wind with the magnetic field, resulting in decreased mass loss from the star, mass loss quenching, and magnetic braking of the star, to understand how that modified stellar evolution. And that's what's being shown here. These are two models of a star that begins its life with the same conditions, but under one hypothetical example, the star is evolving with a surface magnetic field of a few kilogauss, and that's this upper one here. And in the lower example, the star is evolving without a magnetic field. And you can see that there's an appreciable difference between the two. The star with the magnetic field is more massive and brighter as it evolves because it's retaining mass and hence has higher luminosity. And Joel recently published an entire grid of these models. It's a 2022 paper. You can find it on the archive, for masses ranging from a few solar masses up to about 60 solar masses. And in addition to producing the evolutionary tracks and making predictions about the impact of the magnetic field on the star's evolutionary path across the HR diagram, he also makes predictions about how the rotation of the star should evolve, how the magnetic field should evolve, and how the internal chemistry of the star should evolve as a consequence of the slowed rotation. So we already have a theoretical context in which we can start using observations of stellar magnetic fields through stellar evolution in order to make theoretical tests. So with that, I'm going to summarize and finish up. So I've tried to give you a flavor of the work that we've been carrying out, trying to understand the post-main sequence evolution of main sequence B-type stars, both at the Blue Supergiant stage and the classical Cepheids stage. We've now detected magnetic fields that have strengths that are of order 1 Gauss in a sample of a little bit more than a half of a dozen Blue Supergiants, with masses ranging from about 7 to 12 solar masses. And from a preliminary examination of the behavior of their Stokes V profiles, we have the impression that there are likely two different origins of their magnetic fields. So similar to the main sequence, we find some stars that have complex magnetic fields that vary quite quickly, probably dynamo in origin, and we have magnetic fields that are relatively stable and seem to be structured on large scales, similar to fossil magnetic fields on the main sequence. I also described the magnitude limited survey that James Barron is carrying out, studying classical Cepheid variable stars. His first results were published in monthly notices in a dedicated paper about 6 months ago. He has many more observations now and is likely to be publishing something new over the course of the year. Fields are clearly quite common in classical Cepheid stars. The characteristics of their Stokes V signatures, while difficult to understand in many cases, are generally consistent with the presence of dynamo-generated magnetic fields, and that's consistent with their relatively cool temperatures. Polaris in particular is a very interesting object for which we've obtained many observations with the objective ultimately of being able to model its magnetic field structure and potentially its evolution. So we have a whole bunch of next steps. Obviously, we need to expand the samples of these stars. In the case of the blue supergiants, for most objects, we only have 2 or 3 observations. And that's a consequence of the fact that these are stars that are, their magnetic fields are sufficiently weak that they require significant observing time in order to detect them. And also the stars themselves rotate very slowly. And so because they're large stars, the time scale of their magnetic field variation is quite long. And so that means that it needs to be a dedicated long-term campaign. In terms of the Cepheids, I've already talked about the peculiar Stokes V profiles in some of these stars. While we initially saw that as both a surprise and a challenge, it's a useful challenge because my impression is that they're encoding information about atmospheric dynamics that may well not be accessible through other means. Just before I finish off, I'm going to throw in a little advertisement. So we're organizing a residential Congress under the MIAP banner in Munich this coming October, so a year from now. It's 1 month long, and the focus is on stellar magnetic fields from essentially from protostars to the ends of stellar lives. This is a funded workshop, so individuals who come for at least 2 weeks can obtain up to 80 euros a day for subsistence. And it's a selective conference, so people apply for participation, and then ultimately we'll make decisions about who is selected to attend. So if this is something you're interested in participating in, feel free to ask me about it or contact me offline. And with that, that brings me to the end of the talk. Thanks very much for your attention. I'd be happy to take any questions.
Thank you very much. We have time for questions. I have one questions. First is, what is the role of binarity in all those evolution? All these evolutions do not take into account any binary stars, actually.
Okay, so it's a little hard to hear, but my understanding of the question was, what is the role of binarity in all of this?
Yes.
Yes, no, that's a very good question. Because of the kinds of stars we're studying, stars that are extremely bright intrinsically, we tend not to have a whole lot of information about their multiplicity characteristics. Or if we do, then those particular stars tend to dominate the systems because they tend to be quite luminous and quite massive. So I can't really comment on the role of binarity in the particular work that I've been discussing today, but more generally, binarity appears to be an important ingredient in the generation of stellar magnetism or the retention of stellar magnetism. In the case of cool stars, of course, it makes sense that if we have stars in a relatively close binary, then through tidal effects, they're forced to into a synchronous rotation with their orbits. And that generally results in them being rapidly rotating and powering the dynamo quite significantly. And so those tend to be quite active stars. In the case of hotter stars with fossil magnetic fields, observations indicate that there's a relative dearth, that is a lack of stars with magnetic fields in close binary systems. And we don't know why that is. One suggestion has been that it's a clue that fossil magnetic fields are at least in part generated through mergers earlier in their evolution. The idea being that stars that are currently in close binary systems likely didn't undergo mergers because those would have disrupted the binary systems. Whereas stars that aren't currently in close binary systems could well have undergone such mergers. But that's mostly speculative at this point.
Okay, thank you. And my second question was about trying to make the correlation with evolved stars. If you see in the stars that you are studying, if you see any morphological pattern, jets or outflows, things like that, that you could link to the presence of magnetic fields.
So I caught most of the question. Sorry, are you asking me, do we see other energetic phenomena like jets associated with these stars?
Yes, that may be linked to magnetic fields.
Yeah. So the answer is no, but I would say that one example of such a phenomenon would be the X-ray brightening of delta Cephei, right? So that could be one example of a phenomenon that is related to the presence of the magnetic field. But no, these stars their magnetic fields tend to express themselves more subtly.
Okay, thank you.
Another question? Well, I have a question. I saw one of the plots where relate the rotation velocity with age. And I wonder to know if there is a relation in polarization with rotation velocity in the Cepheids.
Right. So if I've understood the question correctly, you're asking, is there a relationship between the intensity of the magnetic field and the rotation velocity? Yeah. So excellent question. Absolutely, in the case of cool stars with dynamos. So you're probably familiar with the so-called rotation activity relation that in its original form expressed chromospheric activity indicator as a function of rotation rate and demonstrated a really significant increase in the intensity of chromospheric activity in more rapidly rotating stars, and in fact revealed the concept of saturation of dynamos. And that's been extended to, for example, X-rays, as well as direct measurements of magnetic fields nowadays. There is no similar relationship for stars with fossil magnetic fields. So as we might naively imagine from the dynamo equation, there is no impact of the rotation of the star on the intensity of the magnetic field in the case where it seems to be a slowly decaying remnant. We find magnetic stars that are almost non-rotating, that have periods of decades, that have strong magnetic fields, and we find other examples of stars that are very rapidly rotating that have quite weak magnetic fields.
Okay, thank you. Okay, thank you very much, and thanks again. Great.
Thank you all very much. I really appreciate the invitation, and I wish you a constructive end to your colloquio.